Hi, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And the purpose of this video module is to talk about some of the ways that we represent digital communication signals. We can think of digital communications as using analog signals to transmit digital information between two devices through some kind of analog channel. And the representation and analysis of these signals is made a lot easier by a couple of different conventions that we use. And these conventions are basically a way of efficiently representing communication signals that tend to focus on the information-bearing properties of those signals and sort of strip away other parameters of the signals that don't carry information. And so the two types of representation that we're going to be talking about in this module are baseband signal representation and signal vector representation. To start off with, baseband signal representation is all about finding an efficient way to represent passband signals. So let's start by considering a passband signal S of t. And a passband signal has a spectrum where the spectrum of the signal has a certain bandwidth, W, and is centered at some frequency offset Fc. And we call Fc the carrier frequency of the signal. And generally speaking, a passband signal carries information by or through changes in either its amplitude or its phase. And those amplitude and phase variations are what cause or what give it the signal bandwidth W. And generally speaking, in order to be classified as a passband signal, the signal bandwidth W is quite a bit smaller than the value of the carrier frequency. And just choosing some typical numbers, maybe from a Wi-Fi signal, we're looking at signal bandwidths on the order of 20 megahertz and a carrier frequency offset of 2.45 gigahertz. So usually the carrier frequency is one or two orders of magnitude larger than the signal bandwidth. By far, the most common example of a passband signal is a wireless signal, but there are other passband signal examples as well, both on wired channels and in optical channels. And so our goal is to represent a passband signal by a second signal that we are going to denote as SL of t with a spectrum centered at DC, or at zero frequency. And this type of signal is what's known as a baseband signal. And you'll see in my drawing here that basically the signal spectrum of this baseband signal is identical to, or has an identical shape to that of the passband signal. And it looks like we've basically just sort of taken that passband signal and shifted it back down to baseband. And basically that's exactly what baseband signal representation is all about. The whole goal is to represent a passband signal with a signal centered instead at baseband. The signal SL is generally referred to as the complex envelope of the signal. The reason for that is, as suggested in my picture, the signal spectrum of the baseband signal is no longer conjugate symmetric around zero. And when that happens, you get a complex signal rather than a real signal. And so in general, this baseband signal is complex. And so our goal is to basically provide or develop a mathematical relationship between the passband signal and this baseband signal, and show that the baseband signal contains all the important aspects of the passband signal. So at the start of our discussion of baseband signals, I suggested that this baseband equivalent signal is formed by shifting the spectrum of the passband signal down to DC. And the purpose of this slide is basically to show mathematically that is exactly what happens. So we define the spectrum of the passband signal, S of f, as being the Fourier transform of the passband signal expression that includes the complex envelope. And so, again, using the identity that the real component of a complex entity is equal to 1/2 the entity plus its conjugate, we expand that expression out into this term, and then we can take the Fourier transform of both of the two terms in this summation separately, and then just add them together. And so what that boils down to is essentially taking the Fourier transform of the complex envelope of the signal multiplied by this exponential term, which essentially shifts the signal in frequency so that it's centered at the carrier frequency. And this is just from the properties of the Fourier transform. You can see this in any sort of standard Fourier transform table. And so if we express the Fourier transform signal in the frequency domain, we see that the spectrum of our passband signal is equal to 1/2 times the baseband signal spectrum, shifted up to FC, plus the conjugate of that spectrum, shifted down to minus FC. We have this factor of 1/2 basically from our real operator, and it allows us to make sure that we satisfy the relationship between the energies of the passband and the signal and its complex envelope. So we know that Parseval's theorem says that the energy of a signal in the time domain is equal to the energy of that signal in the frequency domain, right? That's all we've got written down here. And so the energy of the passband signal is equal to the energy of the first term or the positive frequency term of the complex envelope and the negative frequency term of the complex envelope. We take the energy of those two components, we add them together, and we get the energy of the complex envelope signal, again with this factor of 1/2 in front of it. And so again, I guess what we've done on this slide is we've shown that the passband signal spectrum is indeed the complex envelope spectrum, just shifted up to plus or minus FC, and that the energy relationship between the two signals is maintained in the frequency domain. Now, sometimes at this point there's confusion about this 1/2 energy relationship. Students think that if the baseband signal and the passband signal are supposed to be equivalent, there should be conservation of energy, and the two signals should have the same energy. It's important to stress that the baseband or that the passband signal and its baseband representation are not the same signal. The baseband signal represents sort of the information content of the passband signal, but it's not strictly the same signal. It's not equivalent in terms of energy, and that's why it's okay to have this 1/2 term. Now that we've established a passband signal can be represented at baseband, we now need to move on to the concept of systems. Now, virtually all communications analysis involves taking a communication signal and either passing it through some sort of man-made system like a transceiver or a filter, as well as some sort of natural system like some sort of analog channel, the wireless channel, a wired channel. And the vast majority of these systems and channels can be represented as linear. And because of that, we can represent them as an impulse response, and we'll just represent that impulse response as h of t. And because the systems are linear, that means we can determine the output or the signal at the output by convolving the input signal with this system response. And so what we're going to try to do over the next few slides is to determine whether first of all, we'll define what we mean by the baseband equivalent of a communication system, and then we'll determine whether or not the convolution of the baseband equivalent signal and baseband equivalent system yields the same information as the convolution of the passband signal and system. So let's start by assuming that our passband system, h of f, has a signal spectrum that is centered around plus or minus fc. And let's just define the system response around plus or minus fc as h of l and h of l conjugate. Again, this response is conjugate symmetric because we assume that the passband system response is real. And if we take the inverse Fourier transform of this frequency response, we get some time domain response h of l multiplied by a frequency term and a time domain response hl conjugate multiplied by a frequency term, which we can then express as 2 times the real component of the complex system response multiplied by a complex exponential that just contains the carrier frequency. Again, because we're using this identity. Now, this is going to look super familiar, right? Because this looks exactly like the sort of notation that we use to represent the baseband equivalent signal a couple slides ago, and that's not an accident. But again, the fundamental thing that sort of allowed us to write the system response in this way is just this notion that the frequency spectrum of our passband signal has a response that's sort of centered around plus or minus fc, and that sort of local spectral neighborhood around the carrier frequency is really all we care about. In reality, most practical channels have very wideband system responses. So the wireless channel, a wired channel, optical channels will have system responses that stretch from 0 all the way up to very, very high frequencies. We only approximate it in this sort of passband way because generally we're passing passband signals through these systems so that it's really only the response in a local neighborhood around the carrier frequency that we care about. We don't care about the response of the channel anywhere else because we're not sending a signal over those frequencies, and so we can approximate the response of that system as 0 over those frequencies. So now what we have left to do is to check and see if convolution works. And so let's define the convolution. Let's define the received passband signal. So the passband signal at the output of the passband system, h of t, and when excited by the input signal, s of t. Right? And so remember, the signals that I've underlined at this point are all passband signals, right? So R, H, and S are passband signals, but they're all linear, and so there's no problem with defining the convolution of a passband linear system with a passband signal. And so what we're going to do is, since H and S are passband, R is going to be passband as well. And so we can write R in passband notation, or the passband notation that contains its complex envelope or baseband equivalent signal. And there's nothing unusual or wrong with doing this at this point, because R is just a passband signal like any other, and we've shown in earlier slides that we can write the passband signal in this way. And so the way that we're going to establish that convolution works is actually in the frequency domain. So the frequency spectrum of the passband signal R is just equal to the multiplication of the passband system response in the frequency domain and the spectrum of the input signal. And so what I do at this point is I just expand out the expressions for that passband signal and the passband system as consisting of their baseband equivalent signal spectra centered at plus or minus Fc. And then this part of the expression is just what we get when we multiply, when we basically expand out our brackets. And you'll notice that the cross terms have disappeared. And the reason for that is because we assume that the signal response at plus Fc and the signal spectrum at plus Fc and the signal spectrum at minus Fc don't overlap with each other, and one is 0 where the other one is non-zero, and so those cross terms basically disappear. And so what we have is the baseband signal spectrum of our signal centered at Fc multiplied by the system response, or the baseband equivalent of our system response centered at Fc. And so these two underlined terms are sort of confined to the local spectral neighborhood centered around Fc. And so we can represent the product of SL and HL at plus Fc as a single term RL. Similarly, the conjugate signal component and the conjugate system component centered at minus Fc we can represent as RL. There should actually be a conjugate there. And this means basically that, and then of course what we have here is just the frequency domain, or the frequency spectrum of our original passband received signal, R of t. So what this tells us then, big picture, is that the multiplication of the baseband equivalent signal and the baseband equivalent of the system essentially completely defines the passband frequency response of our received signal. And so that means if this baseband equivalent frequency domain multiplication gives us all the information we need to define the passband signal spectrum of R of F, then it is valid for us to use the convolution of the baseband signal component the complex envelope of the signal and the baseband equivalent response of the system to determine the baseband or the complex envelope of the received signal without any loss of information. And so really this last equation draws to a close our discussion of baseband signal representation. And again, just to sort of summarize what we've done, is we've shown that there is a mathematical relationship between a passband signal and the signal you get when you shift its frequency down to 0. And we've shown that That signal that's centered around 0 contains the amplitude and phase term of the passband signal. That is what carries the information in the passband signal, right? It doesn't carry the carrier frequency, but there's no information in the choice of carrier frequency. And we've shown then that we can also write a baseband equivalent for our system response, and the convolution of the baseband equivalent signal and the baseband equivalent system response gives us all the information that we would get if we were working with passband signals and systems. And that's basically what we have on this final slide here. Now, just to conclude our baseband signal discussion with a quick example, let's consider a passband signal S that has a carrier frequency of 100 kilohertz, a phase shift of pi over 4, and is multiplied by a pulse shape G. And G is basically a triangle that has a width equal to capital T. Now, normally a communication system is multiplied by, normally a communications passband signal contains an amplitude and a phase term that are constantly changing, right, as we use that wave to transmit different information bits over a certain period of time. And usually what we do is we model the variation in the amplitude and phase as random, and characterizing that is something that we're going to be talking a lot, or dealing with those random variations is something we're going to be talking a lot about later on in these video modules. But just for now, to keep things simple, let's assume that G of T is just a constant or a non-random deterministic pulse shape. And so our baseband, our passband signal is G of T multiplied by a cosine with our carrier frequency and our phase term pi over 4. If we express that in the notation where we can see our complex envelope, we have our, if we express that in the notation where we can see our complex envelope, we have our pulse shape G with our phase term pi over 4. Then we have our complex exponential with our carrier frequency. And so our complex envelope is equal to our triangular pulse multiplied by e to the j pi over 4. We can do our energy calculations both on the baseband, or on the complex envelope, and on the full passband signal, and we can see our energy relationships that we've talked about hold. And we can also determine the spectrum of the complex envelope and use that to construct the spectrum of the passband signal as well. And so the spectrum of the complex envelope is just the Fourier transform of SL of t, Fourier transform of the triangular pulse multiplied by the complex exponential. And just using any Fourier transform table, you can see that the complex, or sort of the Fourier transform of a triangle is a sinc squared spectrum. And then the passband spectrum is just 1/2 multiplied by the baseband signal spectrum centered at plus FC, and the baseband signal spectrum centered at minus FC. And then you just get that term there. Okay, now we're going to move on to talk about signal vector representation. And in the coming modules, we're going to see a lot of different types of modulation schemes that create communication signals in all different kinds of ways. And simply drawing these signals, sometimes it's possible, but often it's not. And so we need a more sort of efficient representation for the signals. And also, what you'll find is that different modulation schemes use signals to carry information in different ways. So for example, sometimes we'll change the amplitude of a signal to represent information. Sometimes it'll be the amplitude and phase. Sometimes we'll change the waveform itself, the shape of the waveform itself. And what we would like is a way of representing signals that sort of focuses on the properties of the signals that are being changed to carry information or to represent different combinations of bits, and sort of strip away or ignore the properties of the signals that remain constant, regardless of what information we're trying to send. And as we're going to see, representing signals as vectors in signal space basically does this. And so what we're going to do in this, in the next coming slides, is I'll introduce signal vector representation in a very generic way, but we're going to basically be using it for the rest of these video modules. So it'll be very present in our discussion of modulation, matched filter, signal detection. It's basically going to be the way that we discuss communications from now on. So we'll start our discussion with a bit of terminology. First of all, we'll assume that our modulator is sending n bits per symbol. Now, just as a little bit of terminology, in digital communications we talk about bits and we talk about symbols. And a symbol basically refers to the analog waveform that we're using to represent a group of bits. And so we could say the analog modulated signal, or we could simply refer to that signal as a symbol. And so if we're saying we have n bits per symbol, that means that each analog waveform that we're sending through our analog channel represents a total of n bits. And so the total number of waveforms sent by our modulator is m is equal to 2 to the n. Now, signal vector representation is constructed or is based on the notion of a basis function set that consists of k orthonormal signals. And the notation that we use to denote these signals is fk. And usually k is less than or equal to m. What does orthonormal mean? It means basically that the signals are orthogonal to each other. So if you take any two different signals from an orthonormal set and correlate them together, and by correlate we mean multiply and integrate. So if you take two different signals and you correlate them together, then you get 0. So the signals are orthogonal to each other. And if you correlate a signal with itself, you basically square the signal and integrate it so you get its energy. And when you do that, you get 1. So signals have unit energy. And so that's what it means to be orthonormal. And how do we use these orthonormal basis function signals? Well, basically, every signal created by our modulator, every sort of information-bearing signal, can be created by adding a different combination of these basis function signals together. And that's what we denote with the last equation on this slide. So essentially, each modulated signal, Sm, is a linear combination of the basis function signals. And so we add all our basis function signals together, and each basis function signal is multiplied by a unique weight. And these weights are unique to the particular kind of modulation signal that we are trying to generate. So the first modulated signal is going to have a certain set of weights. The second modulated signal will have a different set of weights, and every unique modulated signal is going to have a different set of weights that are used to sort of control how the basis function signals are combined. Now, how do we come up with these weights? Well, basically, the weights that we put in front of our basis function signals are the projection of each modulated signal onto the basis function space. So if we are, let's say for example, we want to figure out the weight that the second modulated signal needs to put in front of the third basis function. So in that case, m would be equal to 2 and k would be equal to 3. Then we take the second modulated signal, in this example it would be S2 of t, multiply it by the third basis function signal, F3 of t, integrate, and then you get the weight. And that's basically taking the projection of that modulated signal onto that particular basis function. So that's how you generate the weights. Although, as we're going to see when we look at linear modulation, the weights are, you can always calculate them this way, but the weights, the formulas we're going to be used to determine the signal vector weights are often given to us. And so it's basically the weights that define each unique signal. So remember, the basis function signals are constant. They're always the same. For a given modulation, or for a given type of modulation, the basis function signals F1, F2, all the way up to Fk are always the same. The only thing that changes to allow us to generate different signals are the weights that we put in front of those, in front of the basis functions as we add them together. And so since it's the weights that really determine each unique signal, what we do is we take the weights and we gather them into what's known as a signal vector. And so this would be the signal vector for signal Sm of t. And we basically just put whatever signal value it needs for the first basis function signal, whatever signal weight it needs for the second basis function signal, all the way up to k. And so the dimensionality, or the number of elements in each signal vector, is always equal to the number of basis functions, right? And so if we have a modulation scheme that only has one basis function signal, these are one-dimensional vectors. If we have two basis function signals, if capital K is equal to 2, then we have two values in our signal vector. So that would be a two-dimensional signal. If we have three basis functions, it would be a three-dimensional signal. And as long as K is less than or equal to 3, we can draw these signal vectors in a vector space, right? So if our vectors are two-dimensional, we can create a two-dimensional picture. Each signal vector would be a point on that two-dimensional picture, because the values would give us sort of the x and y coordinates. And we would call that diagram a signal vector diagram, or sometimes also a constellation diagram. And we'll be seeing some examples of these later on. It's important to remember, though, that we can have almost any number of basis function signals. And we're going to see an example of a modulation scheme later on called orthogonal modulation that has 64 basis function signals, 128, 256. And so our signals then would have 128 dimensions, or 256 dimensions. And so it's not possible for us to draw those signal vectors, but it's still a very valid modulation scheme. So just to sum up, and this is sort of an important point, remember that the number of basis function signals determine the dimensionality of our signal vectors, because we have to have one value in our vectors for each one of our basis function signals. The number of signal vectors that we have is determined by the number of different modulation signals that we want to generate. And that's determined by m is equal to 2 to the n, where n is the number of bits per symbol that we're transmitting. So if we want to, let's say, transmit 2 bits per waveform, or 2 bits per symbol, then we need a total of m is equal to 4 different signals, which means we would have 4 different signal vectors. And then the number of elements inside those signal vectors is determined by the number of basis function signals that we have in our set. One of the nice features of signal vectors is that it makes determining the energy of a signal very easy. So the energy of the mth modulated signal can obviously be calculated by squaring and integrating, but it's also equal to the squared norm of the signal vector. And the norm of a vector is defined here. So it's basically the square root, there we go, the square root of the sum of the squared values in the vector. So basically you square every single value in the vector, you add them all up, and then you take the square root of the sum. So the squared norm just gets rid of the square root. And so all this means is that if you want to figure out the energy of a signal, you just square the values in its signal vector and add them up. And so why does this work? Well, it can be illustrated actually with an example where we have two basis function signals in our basis function set. And so what I'm showing here is the energy of modulated signal M is just equal to the square of the is just equal to the square of this, the integral of the square of the signal. And then in the second line, I substitute in the basis function equation for that signal. So we have two signals in our basis function set, F1 and F2, each multiplied by their respective weights. Then I just expand out the bracket, and we get three terms basically. This first term is equal to a constant, SM1 squared, multiplied by F1 squared. And so the constant will just come out front, and then we just have the integral of F1 squared. But we know that these basis function signals have unit energy. So if you square them and integrate, you just get 1. And so the integral of F1 squared is just equal to 1. And then all we have left is SM1 squared. Exactly the same thing happens with this term. This term, or the third term in the equation, ends up just being equal to SM2 squared. And what happened to our cross term here? Well, again, these guys are just a constant, so they go out front. And then we have F1 times F2, or the integral of F1 times F2. But remember, because these signals are orthonormal, they have to be orthogonal to each other, right? So if you multiply the two of them together and you integrate, you get 0. And so that just means this cross term goes to 0. And so we end up getting the energy of our signal being equal to the sum of the squared values of our signal vector contents. Another really important concept related to signal vectors is the distance between two signal vectors. And so it's possible to calculate the distance between any 2 points in any vector space just by taking the norm of the difference between the two vector values. And so that's the calculation. But the distance between two signal vector points in digital communications has a very, very important meaning. So the greater the distance between two signal vectors, basically the more different those signals are from each other. Conversely, as two signal vector values get closer and closer together, as the distance between two signal vectors decreases, those signals become more and more similar. They start to look more and more alike. The reason why this is important for us is because when in any digital communications system, when you send your waveforms through a channel, they're going to get corrupted by noise and interference and distortion. And it's the job of the receiver to take this distorted signal and to try and guess which signal was being sent by the transmitter. Now, if two signals look very similar to each other, that means that the chance of confusing them in the presence of noise is going to be higher. And so basically, if the distance between two signal points is small, that means the probability or the chances of confusing those two signals in the presence of noise is going to be higher. If the distance is greater, then the chance of confusing those two signals is going to be smaller. And we're going to use this notion of distance as we talk about receiver design. And as it turns out, maximum likelihood detection in the presence of additive white Gaussian noise is going to boil down to a very intuitive metric that is based on this idea of distance. Okay, the last thing I'd like to do is just finish off with a quick example to sort of illustrate how these basis functions work. Now, as we move on to the linear modulation module, that module is going to be full of basis function examples because we're going to use this notation to introduce every single modulation scheme. But still, it's worthwhile doing a quick example here. And so what I'm going to show you is QPSK, or quadrature phase shift keying, which is a passband modulation scheme where we have 4 different waveforms in our modulated signal set. So in this case, capital M is equal to 4, which means we carry 2 bits per modulated waveform, or 2 bits per symbol. The different signals that we create are just cosine waves with a constant amplitude and a different phase shifts of 45, 135, 225, and 315 degrees. And the basis function signal set is equal to a normalized cosine wave and a normalized sine wave. Now, where did these basis functions come from? Well, there is a technique called Gram-Schmidt orthogonalization, where you can take a set of modulated signals and construct a basis function signal set for them. I'm not going to go into Gram-Schmidt orthogonalization in any detail. I mean, you need to be aware that it exists, but practically speaking, we already know the basis function signals for all of the major modulation schemes that we're going to be using. And so these signals are basically given to us. And so I won't bother showing this, but you can satisfy yourself that if you square either of these two signals and integrate, you'll get unit energy. And if you multiply the two signals together and integrate, then you should get 0. And I should say that your integral would be from 0 to t, where t is the duration of our modulated symbol interval. The signal vectors can be calculated by taking the projection of each signal waveform onto the basis function signals. And so you can use this equation to determine the signal vector values. Again, in this case, it would be from 0 to t that you'd be doing your integral. Once we get into the linear modulation section, I'll just basically give you a short form for coming up with these signal vector values. But you can do it with this calculation as well. And if you do, these are the 4 signal vectors that you end up with. Again, we have 4 signal vectors because we have 1 vector for every signal in our modulated symbol set. So because m is equal to 4, we have 4 signal vectors. And because k is equal to 2, each of these vectors have only 2 values in them. So it's a 2-dimensional vector space that we're working with. And because it is 2-dimensional, it makes it very easy for us to draw. And so we can produce a signal vector constellation diagram where each of the signal vectors are a point in vector space. So this is S1, this is S2, S3, and S4. The x and y values of each of these signal vectors are just equal to the values, or sorry, the x and y values of each point are just equal to the values from the signal vectors. The distance from the origin is a root 2 over t, and we have 4 points because we have 4 signal vectors. You'll notice that the distance between each of these points is not equal. So the distance between these 2 points is less than the distance between these 2 points. And that means that in a noisy environment, we are more likely to mistake, if we transmit signal S1 in a noisy environment, we're more likely to mistake S1 for S2 or S4 than we are to confuse S1 with signal S3, because it's a greater distance apart, which means that it looks different. And so that's all I want to say at this point for signal vector representation. But as I said, once we get into the linear modulation section, you're going to be seeing this notation a lot more. We're going to be using it basically constantly from now on.